So multiplicity, which is this chunk right here. Okay? And there's a couple ways that I like to do this. So for one, here's our Clebsch-Gordon series, right? And these little S's correspond to the electrons, okay? And S can only be 1/2 for an electron, right? So when you start going through these possibilities, depending on the number of electrons that you get, there's only certain values that you're going to have. Basically 1 or 1/2 or 0. Okay? So let's go through that. And so this is for any 2 electron system. Okay? So we have singlets, doublets, triplets. Or, not any 2 electron system, my bad. Any 1 or 2 electron system. Because a doublet is a 1 electron system. Okay? So if we have a singlet, we know that a singlet describes a paired up set of electrons. Okay? And if you go and calculate S for this situation, you get S to be equal to 0. Oh, so excuse me. So S plus or minus 1/2, right? Okay. So both of those cancel out. S is equal to 0. And if S is equal to 0, 2 times 0 plus 1 is 1. And so on my main term here, if I wrote 1, and then I'm just going to write L and J, that number 1 tells me I have a singlet. So we don't have to do this 2s plus 1 if you already know the electrons are paired. If you already know the electrons are paired, that's a singlet, and we can automatically just put a number 1 right there. If we have a doublet, S is equal to 1/2, right? Only 1 electron. And so 2 times 1/2 plus 1 is 2. All right? So there's our doublet. That would just describe a singly unpaired electron. And so we would automatically just write a 2 right there, L and then J. And then obviously we would have a P or another letter for the main other terms. Okay? And if we have a triplet state, we have 2 electrons plus 1/2 plus 1/2. So I'll note that just as this. It could certainly be minus 1/2 and minus 1/2, but we take the absolute value. And so what that means is, yes, we would then have S is equal to 1. 2 times 1 plus 1 is 3. And so literally, if we knew that it was 2 unpaired electrons, we wouldn't even have to go through this. We could just write triplet as a 3. 3 triplet means the same thing. Okay? So now finally, what about the J value? Well, J also has a Clebsch-Gordon series, which is given by all values capital L plus capital S all the way down to L minus S. And so that means if you have a situation where you have like D, P, and S as possibilities, you get an awful lot of possibilities for the J value, okay? So I'll go back to those P2 examples we used, right? We looked at 3 different P2 examples given by this, okay? And let's just go through all of those. So we remember now that when they're both paired up, D is the main term, which comes from an L equal to 2. When they were split all the way like that, oh wait, let me double check, apologies. Yes, so S, because it was -1 and +1, so that cancels. Okay, so this is the S term from L equal to 0, and this was our P term from L equal to 1, okay? So now that means in my terms, if I look at this here, so this is a triplet, right, because they're unpaired. So I could write that as triplet P. And now, because I've specified the fact that it's a triplet and a P, right? So triplet corresponds to S equal to 1. So then I could get a triplet P 2 as my term symbol. However, I could also have a triplet P1 and a triplet P0. And as it turns out in spectroscopy, the 2, 1, and the 0 state for that don't really matter all that much because we don't have any spin-orbit coupling, spin-orbit splitting to deal with over here, okay? Well, I suppose that's only partially correct. So because, in fact, if both of those electrons were both spin down, then that would be important. So what I meant to say was the triplet P1 state becomes less important because it's this triplet P2 that's really describing both of them being up, and the triplet P0 that's really describing both of them being down. However, these still really aren't observed to create splitting that we observe in doublet states when you only have one possibility, okay? So now if we go to these S possibilities here, we recognize that it's an S. It's still a triplet, okay? So now that means, so S is equal to 1 and L is equal to 0. So the only possibility is, or excuse me, there are two possibilities, 3s1 and 3s0. And now finally, if we look at this D state, we've got the letter D right there. We recognize that this is now a singlet because they're paired up. So S is equal to 0. And so now I could have a singlet D2. I could have a singlet D1 and a singlet D0. Okay? And so once again, we typically for, I'll say for the non-half values of J, that value is less important. So when we see a non-half integer of J, and all of these are non-half integers of J, oftentimes people just discard that term right there because it's less important for spectroscopy. However, when we do have J 3/2 or J 5/2 or J 7/2 even, those terms are important and they're often included, okay? So what I want to do, I've got several examples to go through, and I've already been talking for about 28 minutes. So I'm going to stop this video, and I'm just going to record another video going through all of these possibilities, or at least some of them. I'll go through a big chunk of them, and the terms that we get, okay? So I'll see you in the next video for going through examples of these term symbols.